picture this. You're standing on a city curb,
Right.
and it is just absolutely pouring rain. I mean, the wind is howling, your umbrella is basically useless, and you are freezing to the bone.
We've all been there. It's miserable.
Exactly. It's the worst. So you pull out your phone, shielding the glass screen with your hand so it doesn't get totally soaked, and you tap that little black button, the one that says request ride.
Yeah.
Now, think about what happens next. Within, I don't know, maybe 3 seconds, the screen shifts. It just casually says searching for driver.
Just a few seconds. Yeah.
And it feels like magic, right? It feels
Yeah.
completely instantaneous. But in those 3 fleeting seconds, a massive, just mind-bogglingly complex digital universe has literally exploded into action all around the world to make that happen.
It really is an explosion of activity. And it's funny because we take that smooth 3-second transition completely for granted. I mean, we just expect the car to show up.
Oh, totally. We get annoyed if it takes 5 seconds.
Right. But behind the glass of your phone screen is this, well, it's a symphony of computer engineering. The sheer volume of decisions, validations, and, intense calculations happening before your thumb even leaves the glass is staggering.
And that is exactly our mission today. We are going to explore that invisible universe. So, okay, let's unpack this, because we've actually got our hands on the back-end architectural maps for this deep dive.
The actual blueprints.
Yeah, the literal blueprints that dictate how a company like Uber orchestrates this absolute chaos. And look, I know when we start talking about system architecture or back-end workflows, it can sound, well, it sounds like dense software engineering.
It sounds very dry, like a textbook.
Exactly, like a textbook. But as we dig into this, it is actually a thrilling story about preventing absolute catastrophic disaster.
That's honestly the best way to frame it, because this isn't just about ride sharing.
Right.
It isn't just about how a specific company gets a sedan to your curb in the rain. It is a masterclass in how to build massive failure-proof systems that run our modern world.
Like everything uses this.
Everything. Whether you are, ordering a physical product online or streaming a live sport event to millions of people, or even executing high-frequency stock trades. The principles we are going to look at today are the exact same principles keeping the entire digital economy from collapsing under its own weight.
Wow. Okay, so let's start at the very beginning. You're on that rainy curb, and you've just tapped the button. Your phone sends a signal.
The initial request.
Right, the blueprints call this the initial HTTP request. And it flies through the cellular network, hits a massive data center somewhere, and encounters something called the gateway.
The gateway, yes. Step 1.
Now, I'm trying to visualize this layout, and I have to ask, why put a gateway there at all?
What do you mean?
Well, why doesn't my phone just talk directly to the specific computer that finds the cars? It feels like, I don't know, walking into a massive corporate skyscraper, right?
Yeah.
And you know exactly who you want to see. Let's say you need to see Dave in accounting on the 40th floor.
Okay, Dave in accounting.
Yeah, but instead of just jumping in the elevator and going straight to Dave, you are forced to stop, wait in a long line, and talk to the front desk security guard. Isn't that just creating an unnecessary bottleneck right at the front door?
Well, it might feel like a bottleneck to you, the individual walking into the building, because like you said, you just want to see Dave.
Right, I'm in a hurry.
Exactly. But from the perspective of the skyscraper itself, that front desk is the only thing preventing total anarchy. The gateway acts as the ultimate bouncer and traffic cop.
Okay, a bouncer?
Yeah. And what's fascinating here is that the gateway doesn't actually know how to fulfill your ride request. That is not its job at all.
Wait, really? It can't find the car?
It couldn't find a car if its life depended on it. Its job is to handle what engineers call cross-cutting concerns.
Cross-cutting concerns. Okay, so meaning things that absolutely every single request has to deal with, no matter what it's actually asking for.
Exactly. Think about everything that has to happen before the system even cares that you want a ride. Let's break it down. First up, authentication.
Like checking my ID.
Right. Are you a real user? Is your session token valid, or are you, say, a malicious script trying to probe the system for vulnerabilities? The gateway checks your digital ID first.
Makes sense.
Second is rate limiting. Are you tapping that request button 50 times a second because your phone screen glitched in the rain?
Which happens to me all the time, honestly.
Right. Or, alternatively, are you part of a coordinated botnet trying to launch a denial-of-service attack to take down the entire global network?
Oh, wow. So it has to tell the difference between a glitchy wet screen and a hacker.
Precisely. The gateway tracks how fast you are knocking on the door. And then third, routing. Which internal service, among the literally thousands of microservices running in this massive data center, is actually supposed to handle this specific type of request today?
But wait, let me push back on that. Why can't the individual departments just handle that? If I just go straight to Dave in accounting, why can't Dave just, check my ID, make sure I'm not spamming him with tax requests, and then do my taxes?
Because then you are forcing Dave to be a security guard instead of an accountant.
Ooh, yeah, Dave wouldn't like that.
Nobody would, and it's not just Dave. If you bypass the gateway, every single back-end engineering team, I mean the team building the ride matcher, the team building the payment processor, the team building the receipt generator.
They'd all have to do it.
Exactly. Every single one of them has to write, test, and manually maintain their own authentication, security, and rate-limiting logic into their specific code.
Oh, I see. That sounds incredibly inefficient.
It's a complete nightmare for maintenance. I mean, think about it. What if a new security vulnerability is discovered globally? A massive zero-day exploit.
Right.
If you don't have a gateway, you have to coordinate a complex security patch across hundreds of different teams and thousands of servers simultaneously, just praying that none of them make a typo or a mistake.
That sounds impossible.
It basically is. By centralizing it at the gateway, one dedicated security team owns that logic. If there's a vulnerability, they patch it in one place, right there at the front door, and the entire ecosystem inside the building is instantly protected.
So it's a shield for the whole company.
It is. Plus, it gives the company one single, unified place to monitor traffic patterns across the entire globe. It's really the central nervous system for incoming signals.
Okay, that makes perfect sense. The gateway is the bouncer. We showed our ID, we proved we weren't a bot spamming the door, and we are officially allowed inside.
You're in the building.
Right. But here is where the blueprints show something really interesting happening with how our phone communicates. It transitions into something called a Writer WebSocket service.
Ah, yes. The WebSocket.
Now, I think everyone listening knows that feeling of opening a modern app and watching it just magically update in real time. You don't have to keep pulling the screen down with your thumb to refresh the page.
Right, it's just fluid.
Exactly. The little car icon just glides up the map. The ETA changes from like 4 minutes to 3 minutes seamlessly.
And that seamless magic is entirely due to the WebSocket. But to understand why it's such a crucial architectural choice here, we really have to look at the limitations of how the internet traditionally operates.
Which is the standard HTTP request, right?
Exactly. Standard HTTP.
Right. That's the classic web. I type in a website, I hit enter, the page loads. The way I've always thought about it is that it's kind of like writing a letter. I put a stamp on it, drop it in the mail, and then I just, sit and wait by my mailbox.
A very slow process.
Yeah. And eventually the server gets the letter, reads it, writes a reply, and mails it back to me. Once I read that reply, the transaction is totally over. We are done talking.
Precisely. It is a strictly request and response model. You open a connection, you ask a specific question, the server gives you an answer, and then it violently slams the door in your face.
Violently slams it. I love that.
Well, it does. The connection is completely severed. It's closed. So if you want to know if anything has changed a second later, say, you want to know if the driver has turned the corner, you have to write a whole new letter, establish a whole new secure connection, send it, and wait for the door to open again.
And that process is what they call polling. Right?
Yes, exactly. Polling.
Which, if you're doing it every single second, sounds absolutely exhausting for everyone involved.
It is incredibly resource intensive. I mean, think about the overhead. If your phone had to ask the servers every single second, have you found a driver yet? How about now? Are they closer? How about now?
Like a kid in the backseat of a car.
Exactly like that. Your phone is constantly doing this complex cryptographic handshake to open secure connections over and over. You would drain your battery in minutes. You would eat up your cellular data plan. And from the company's perspective,
They're getting hammered.
right, you would be bombarding their servers with millions of useless, repetitive questions.
Just a chorus of millions of phones yelling, "Are we there yet?" at the data center all at once.
It would bring the system to its knees. So a WebSocket changes the paradigm entirely.
Okay, so if HTTP is sending a letter and waiting for a reply, a WebSocket is more like calling someone on the phone. They pick up, and instead of hanging up after you ask one question, you both just agree to leave the phone line open.
I like that analogy.
Yeah, you just put the phone on the kitchen counter, off the hook. You don't have to keep dialing. You can just go about your business. And the server can just start talking loudly through the speakerphone whenever it actually has some news to share.
That is exactly how it works. The connection is persistent. It is a two-way street. As soon as you pass through that gateway, the system registers your open phone line with this Writer WebSocket service.
Okay.
And from that millisecond on, the server has a direct open pipe right to your screen. It doesn't have to wait for you to ask a question.
This is why the car actually crawls up the map.
Yes. If we connect this to the bigger picture of user experience, this persistent connection is the secret sauce. The server is just constantly whispering coordinates down that open phone line. He's at the corner. Now he's turning. Now he's 50 feet away.
And my app doesn't have to do any work. It just listens.
Exactly. Your app just listens and moves the little car icon accordingly.
It's a massive shift in how we think about data, honestly. It's the design principle of real-time pushover polling. The system is basically saying, look, stop asking if we're there yet. Save your battery, save your energy. We promise we will tell you the very second we know.
Right. You always want the system to push data to you. You never want to force the client to beg for it. It is vastly more efficient for the server, and it creates that fluid, magical experience for the user on the curb.
Okay, so we are through the front door, the bouncer let us in, and we have this persistent open phone line established. We are inside the building. Now, looking at the map, we hit a massive intersection in the architecture.
This is where it gets really good.
Yeah, the gateway takes our validated ride request and drops it into a system called Kafka. Now, the documentation describes Kafka as a, quote, distributed event streaming platform.
Bit of a mouthful.
Yeah, and I'll be honest, that sounds like the heaviest, most intimidating jargon imaginable. It sounds like something a cyberpunk villain uses to control the city mainframe.
It does sound deeply technical, and it can definitely be intimidating to learn at first. But Kafka is arguably the single most critical architectural decision in this entire system design.
Really? The most critical.
Oh, absolutely. Without it, the whole thing falls apart the moment something goes wrong.
Well, let's play with that because a huge question immediately popped into my head when I was looking at how this is laid out. So I'm standing in the rain. I've requested the ride. The screen says searching for driver.
Right, you're waiting.
We know that finding a driver isn't instant. What happens if, right at that exact moment I'm waiting, a server rack in the data center somewhere just catches fire? Or, I don't know, a maintenance worker unplugs the wrong cable? Or the specific software running the search algorithm just hits a bug and crashes hard?
The chaos scenario.
Yeah. Why doesn't my request just disappear into the digital void? Why don't I get a giant Air 404 on my screen forcing me to start all over again?
What's fascinating here is that you've just intuitively identified the exact catastrophe that Kafka was built to prevent.
Oh, really?
Yes. To understand why it's genius, let's look at the alternative first. Let's look at how systems used to be built before event streaming.
Okay, lay it on me.
Imagine if the gateway, right after authenticating you, operated synchronously. It picks up the phone, directly calls the ride matching department, and says, hey, matching service, find a car for this rider.
Okay.
And then the gateway just stands there on the line waiting for an answer.
Like the HTTP letter waiting for a reply we talked about. It's just blocking everything else.
Right. It waits. And as we know, finding a driver takes time. It could take 2 seconds, or if there's heavy traffic or high demand, it could take 2 minutes.
Which feels like a lifetime in the rain.
Exactly. But while the gateway is waiting on hold, your app is blocked. The whole chain is locked together. Now, introduce your chaos scenario.
The server fire.
Yes. If that matching service catches fire and crashes while it's searching, say it runs out of memory and has to reboot, the connection breaks.
The phone line just goes dead.
The line goes dead. The gateway, still standing there holding the phone, gets a severe connection error. The gateway has no idea what to do. It doesn't have the capacity to fix it, so it throws an error back down that WebSocket to your phone.
Oh, man.
Your screen flashes red, the request is gone forever, and you are left standing in the rain, furiously swiping the app closed and opening it again, cursing the company.
So it's brittle. If one link in the chain breaks, the whole process just shatters. How does Kafka actually solve this?
By entirely decoupling the request from the fulfillment.
Decoupling. Okay.
Right. When your request hits the gateway doesn't call the matching service at all. It doesn't want to talk to them.
Wait, it doesn't? Then how do I get a ride?
Instead, it packages your request into a little digital envelope called an event. An event is simply a factual, immutable record of something that just happened in the past.
Like a timestamp note.
Exactly. It says, hey world, Rider 123 just requested an UberX at these specific coordinates at 4:02 p.m. It takes that event and publishes it onto this massive digital conveyor belt called Kafka. And then, and this is the absolute most crucial part, the gateway immediately moves on. It washes its hands of the entire situation.
Wait, hold on. It doesn't wait for an answer? It doesn't verify that a car was actually found for me?
It doesn't wait for a single microsecond. It drops the message on the Kafka conveyor belt, turns around, and whispers down that open WebSocket to your phone. Got it. We're working on it.
Oh, wow.
That is exactly why your screen instantly transitions to searching for driver in 3 seconds. The gateway has acknowledged the event. It did its job.
But where did the message go?
Now, inside Kafka, the moment that event hits the conveyor belt, it is immediately saved to a physical hard drive. It is persisted to disk, and not just one disk. It is duplicated across multiple different physical servers for ultimate safety.
Ah, so it's not just floating in volatile computer memory like RAM where it could vanish if the power goes out. It's written down in ink. It is physically stamped onto a drive.
Exactly. It is safe. So now, let's look at the ride matching service, the actual brain that has to do the heavy mathematical lifting of finding the car.
Right, the guys the gateway refused to wait for.
Yep. It acts totally independently. It comes along, connects to Kafka, and pulls that event off the conveyor belt at its own pace.
And here's where the fire scenario totally changes, doesn't it?
Right, because if the matching service suddenly catches fire and crashes right in the middle of searching for your driver, it doesn't matter.
It doesn't matter.
Not to the rest of the system. The gateway doesn't care because it's not waiting. Your phone doesn't crash because your WebSocket is still happily connected to the gateway. And your event, it is still sitting safely on Kafka's hard drives.
It's like an indestructible answering machine.
Precisely. It's an indestructible answering machine. When the engineers reboot that matching service, or more realistically, when an automated backup server instantly spins up to take its place, the new server just connects to Kafka and says, okay, where did the last guy leave off? Ah, here is an event. Writer 123 needs a car.
And it just starts over.
It picks up the event and starts the search process from scratch. You, standing on the rainy curb, never even know the data center was on fire. Your screen just keeps saying searching for driver, maybe for just a few seconds longer than usual.
That is incredible. The request is completely divorced from the execution. I asked for a ride, and Kafka basically acts as this massive buffer, this shock absorber that securely records the request so the rest of the company can process it whenever they are actually ready.
That is the absolute essence of event-driven architecture. You trade an immediate synchronous response for massive system-wide resilience. If things break down downstream, the upstream systems just keep taking orders and putting them on the belt.
And as I look at how this Kafka stream is laid out in the blueprints, I notice another massive advantage. The diagrams show these little groupings connected to Kafka called consumer groups.
Yes.
There isn't just one arrow pointing away from Kafka toward the ride matcher. There are multiple arrows pointing to completely different parts of the company.
And that highlights the other superpower of Kafka. It is not a traditional message queue.
Wait, what's the difference? A queue is a queue, right? Like a line at the grocery store?
Well, not exactly. In a standard message queue, think of it like taking a number at a busy deli counter.
Okay, I have ticket number 5.
Right. Once you pull ticket number 5, you have it. You hand it to the butcher, they make your sandwich, and they throw the ticket in the trash. No one else can have ticket number 5. The message is consumed, and it vanishes from the system.
They're gone forever.
Gone forever. But Kafka is an event stream. The events aren't destroyed when someone reads them. They stay there on the hard drive for a set period of time, maybe days.
Oh, I see.
So those consumer groups you saw, they represent entirely independent back-end teams and services inside the company that can all read the exact same event at the exact same time without interfering with each other at all.
So, wait, who else wants to know I asked for a ride, besides the service that's trying to find me a car?
Well, think about a massive global tech giant. You need massive situational awareness. The ride service consumes the event to find you a driver. But simultaneously, a completely separate analytics service consumes that exact same event to update a live dashboard at corporate headquarters, showing a sudden spike in demand in your specific zip code because it just started raining.
Oh, wow. So some executive in a boardroom is seeing a dot light up because of my tap.
Exactly. And at the very same millisecond, the fraud detection service consumes the event.
Fraud. Why fraud?
It looks at your GPS coordinates, your account history, and the device ID of your phone to see if this request matches the behavioral pattern of a stolen credit card.
That's wild. So one single action, me tapping a button on a cold street corner, fans out into a dozen different background processes.
And the beauty is, none of them have to talk to each other. The ride service doesn't have to wait for the fraud team to finish running their complex machine learning algorithms. The gateway doesn't even need to know that an analytics dashboard exists.
That's all decoupled.
Right. The gateway just shouts into the void, "A ride was requested," and anyone in the company who cares can tune into that radio broadcast and listen. Engineers call this fan out without duplication.
Fan out. I love that term.
It is incredibly elegant because you can add entirely new teams to the system later, maybe a new experimental machine learning team, and they just plug into Kafka and start listening to the stream without changing any existing code.
Okay, so the event is on the stream, it's fanned out, the shock absorbers are working perfectly. Now we need to follow the path of the actual ride itself. The architecture maps show the ride service pulling my event off that Kafka conveyor belt. The documentation explicitly calls this component the brain that owns the entire life cycle of the ride.
Yes. If Kafka is the nervous system passing messages around the body, the ride service is the frontal lobe. It manages the state machine of your journey.
State machine, let's ground that. What does that actually mean in this context?
A state machine just means the system progresses through a strict, predefined set of statuses. Your ride starts in a requested state, then it moves to a matching state, then driver en route, then arrived at pickup, then in progress, and finally completed.
There's a rigid timeline.
Exactly. The ride service is the ultimate authority on what state you are currently in.
Okay, but wait. As I trace the lines on this blueprint, I'm noticing a massive contradiction here. Yeah, we just spent 10 minutes talking about how brilliant it is that the gateway uses Kafka to do everything asynchronously. You know, dropping the message, not waiting for an answer, preventing crashes. But right here, alongside the Kafka path, there's a bold, direct line bypassing Kafka entirely.
Ah, I see what you're looking at.
It goes straight from the gateway to this ride service brain. It's a direct, synchronous request and response path. If we just established that async event streams are the safest way to do things, why build a direct telephone line right next to it? Feels like we're breaking our own rules.
It does look like a contradiction on paper, I'll give you that. But in practice, it's a masterclass in pragmatic engineering.
Pragmatic how?
Well, asynchronous event streams are brilliant for tasks that can happen in the background, things that take an unpredictable amount of time, like searching through a whole city for a car. But ask yourself this. When you are requesting a ride, are there things you absolutely demand to know before you actually commit to standing in the rain waiting?
Well, yeah, obviously. I want to know how much it's going to cost, the upfront fare estimate. I mean, if it's surging and costs $100, I might just walk to the subway.
Exactly. And the system also needs to validate that your pickup location is actually on a real road in a city they service and not, say, in the middle of a lake because your phone's GPS glitched. You need that information immediately.
Ah, I see the problem. If everything went through Kafka, the gateway would drop a message saying he wants a fair estimate. And then my app would just hang there for 5 seconds while it waits for a background process to eventually pull the message, do the math, and send it back.
Yes. And a 5-second wait just to see a price, that is a terrible user experience. People would close the app. The rider needs an absolute answer right now before the ride request is even officially created in the system.
So they have to break the async rule.
Right. So for these specific tasks, the gateway uses that direct synchronous line. It makes a direct call to the ride service. Give me a price for this route right now. The ride service calculates it, sends it straight back, and the gateway shows it on your screen.
And it only uses Kafka after I accept the price.
Precisely. Only after you look at the price, agree to it, and hit confirm does the gateway drop the actual find me a car event onto the Kafka stream.
Okay, so you use the right tool for the right job. Synchronous for immediate user decisions, asynchronous for heavy background lifting. That makes complete sense. Which brings us to the next fascinating detail in the map.
What's that?
Well, while this ride service brain is doing all this calculating to get me a fair estimate, the maps show it reaching completely outside of the company's internal network. It calls an external third-party mapping service.
It does, yes, like Google Maps or Mapbox.
Now, I'm thinking about this, and it feels a bit like, okay, imagine a world-renowned master chef at a 3-Michelin-star restaurant. He spends hours perfectly sourcing the meat, creating the most complex sauces, controlling every single element of the dining experience. But when you look in the kitchen, you realize he's deciding to buy his dinner rolls from the amazing little bakery down the street, rather than growing his own wheat, milling his own flour, and baking the bread in-house.
That is a perfect analogy, and in the tech world, insisting on growing your own wheat when a world-class bakery exists next door is a recipe for bankruptcy.
But I want to push back on this because we are talking about a multi-billion-dollar tech giant. I mean, they have infinite resources. Doesn't relying on an external API create a massive single point of failure? What if the mapping bakery down the street goes out of business or their servers crash? Why wouldn't a giant company just build their own maps to control the whole stack?
Because you have to define what your core business actually is. Building a global road network is not a ride-sharing problem. It is a mapping problem, and it is insanely difficult and expensive to solve.
Is it really that hard? They have the money.
Think about what it entails. You have to map every single street on planet Earth. You have to maintain real-time traffic data, track unexpected road closures, know which streets are suddenly one-way because of construction, and understand turn restrictions at specific intersections at specific times of day.
Right. You'd need fleets of cars with cameras driving around constantly.
Yes, you would spend billions of dollars and years of time just to recreate what companies like Google or Apple have already perfected over 2 decades.
So it's just not worth it.
Exactly. The pragmatic engineering choice is to treat specialized external APIs as reliable dependencies. You pay the bakery for their excellent bread so your engineers can focus entirely on cooking the steak, which in this case is the incredibly complex marketplace dynamics of matching riders and drivers efficiently.
But what about the single point of failure? I mean, what if the third-party map goes down? You can't just stop the whole business.
That's where you build in fail-safes. Engineers call them circuit breakers.
Like in a house.
Similar concept, yeah. If the external map API starts timing out or throwing errors, the system detects it and instantly trips a breaker. It stops asking the external service for live traffic routes and falls back to a simpler internal straight-line distance calculation just to keep the business running until the map service comes back online. The estimates might be slightly less accurate, maybe off by a minute or two, but the app doesn't crash. You can still get a ride.
Okay, so they are master orchestrators. They pull in external map data, calculate the price, send it back to me. Now, as all this is happening, the architecture shows the ride service constantly communicating with a massive database. It's writing things down. Rider ID, GPS coordinates, status updates.
Yes, the database is the anchor of reality. It's the durable source of truth for the entire company.
But wait, didn't we just spend 20 minutes talking about how Kafka writes things down to physical hard drives so they are safe?
We did.
So why do we need a completely separate database if Kafka already recorded everything? Isn't that just redundant?
That is a great distinction to make. It's not redundant. They serve entirely different purposes. Kafka is a ledger of events. It is a chronological history of things that happened in the exact order they happened. Ride requested, then price accepted, then search started. It's like a running transcript of a conversation.
Yeah.
But a relational database, something like PostgreSQL, which is famous for its strict data integrity, stores the current state of reality in a highly structured, easily queryable way.
How does that play out in practice? Give me an example.
Let's say you open your app and want to see your receipt from a ride you took in Chicago 3 years ago. The system doesn't want to rewind and replay 3 years of Kafka events, sorting through billions of global messages just to figure out what your final fare was. That would take forever. It'd be like reading a whole diary just to find out what you had for lunch on a Tuesday.
Right, that sounds exhausting.
Instead, it just queries the relational database. Show me the final structured row for ride ID 999. It grabs it instantly.
So Kafka is the live newsfeed, but the database is the final organized filing cabinet.
Exactly. And it is fiercely durable. It guarantees what we call ACID compliance, which ensures that transactions are processed reliably and completely.
ACID compliant.
Right. If every in-memory cache, every web server, and every Kafka node in the entire data center somehow melted down simultaneously.
The ultimate doomsday scenario.
Yeah, as long as the hard drives of this main PostgreSQL database survived, the company could rebuild their entire reality from scratch. They would know exactly who was in what car, who owed what money, and who was waiting on a curb at the exact moment of the crash.
Wow. Okay, so the Brain the Ride service has validated my request, got the map data, saved the official record to the filing cabinet, and now it needs to actually find me a car. We are finally hunting for a driver.
A fun part.
And this is where the architecture gets wild, because we introduce queues, extremely fast memory caches, and some serious geospatial math. The ride service takes all my info and pushes a find a driver job to a specific driver assignment queue.
Here we see our second major layer of decoupling.
But why do we need another queue? We already used Kafka to decouple the gateway from the ride service. Why is the ride service now handing this off to something else entirely?
Because ride creation and driver matching fail in completely different ways, and they operate on completely different timelines.
Walk me through that. What do you mean?
Think about the timeline. Validating your ride, getting a fair estimate, checking if your credit card has funds, all of that is mostly deterministic. The computers can figure it out in a few milliseconds, but finding a driver.
That involves real people.
Exactly. That is an inherently chaotic, real-world process. It requires searching through thousands of moving targets, running complex algorithms to predict ETA through traffic, and then, the most unpredictable part of all, sending a signal to a human being in a car and waiting for them to look at their phone and press accept.
Right. The driver might be looking at the road or changing the radio station or talking to someone. They usually have, what, 10 seconds to accept?
Around that, yeah, so that process could take 10 seconds, or it could take 2 minutes if the first driver declines and the system has to go find another one.
Right.
If the main ride service tried to manage that waiting game itself, it would get completely bogged down. Its internal memory would just fill up with thousands of tasks just waiting on humans to tap screens.
It would become a massive bottleneck for the whole system.
Precisely. It would freeze.
Yeah.
So instead, the ride service packages up all the validated info, your location, your destination, the fact that you requested an Uber XL, and drops it into the specific driver assignment queue.
It delegates.
It delegates the hard labor. It basically says, hey, driver assignment service, here is a valid job. Go hunt for a car. Let me know when you catch one. And the main ride service goes right back to managing other riders' state machines. It keeps the line moving.
Okay, so the driver assignment service picks up the job. It's the hunter. Now it has to actually locate a car near my rainy curb. To do this, the architecture shows it querying something called the driver location cache.
Yes.
Now, looking at this, I have to ask another naive question. We literally just talked about the main PostExpal database. We called it the anchor of reality.
So the filing cabinet.
Yeah, it has everyone's data. Why can't the assignment service just search that main database to find where the cars are?
This is one of the most critical turning points in all of system design. The decision not to use the main database here comes down to one terrifying word for back-end engineers: volume.
Volume. How much volume are we actually talking about here? Let's do the math.
Okay, think about a major city like New York or London. Let's say there are 10,000 active drivers on the road right now.
Just in one city.
Just one city. In order for the system to know where they are, every single one of those drivers' phones is pinging its exact GPS coordinates up to the server every 3 seconds.
Okay, so 10,000 drivers pinging every 3 seconds. That means the server is receiving over 3,300 location updates every single second.
Exactly. Now multiply that globally across hundreds of cities. You are talking about tens of thousands, maybe hundreds of thousands of updates per second.
That is absurd.
It is. Now, a traditional relational database like Postgres is brilliant at maintaining structured, durable data like your ride receipts. But remember, to make data durable, it physically writes it to a spinning hard drive or a solid-state drive.
And writing to a physical drive takes a tiny fraction of a second.
Right. And if you try to force a traditional database to endure tens of thousands of writes every single second, just to update GPS coordinates that are going to be completely obsolete 3 seconds later.
Wait, the hard drives would melt down.
Literally, the disks would not be able to spin fast enough. The input-output capacity would totally max out, the database would lock up, it would crash, and the entire global system would go completely dark.
Just from cars saying, I'm here.
Yes, you cannot put ephemeral, high-speed telemetry data into a durable relational database. It is simply the wrong tool for the job.
Ephemeral, meaning data that is fleeting. Data that literally doesn't matter 5 seconds from now.
Right. Does the system care exactly what latitude and longitude a specific driver was at 2:04 p.m. on a Tuesday 3 weeks ago?
No, not at all.
No. It only cares where they are right this exact second. So instead of a database, they use an in-memory cache.
And the documentation mentions something called Redis for this.
Yes, Redis is the industry standard here. An in-memory cache stores data in the computer's RAM, not on a hard drive.
And RAM is super fast, right?
RAM is exponentially faster. It can handle hundreds of thousands of reads and writes per second without breaking a sweat. So all those driver phones pinging every 3 seconds, they are just constantly overwriting their own coordinates in this lightning-fast RAM cache.
Okay, that solves the speed problem perfectly. But how does it actually find the car near me? I mean, the cache just has a massive list of 10,000 coordinates. Does the server just read the whole list from top to bottom and run the Pythagorean theorem on every single driver to see how far away they are?
If it did that, it would still be way too slow. Math takes time. This is where the absolute magic of geospatial indexing comes in.
Geospatial indexing.
Yes.
Yes.
The cache isn't just a dumb list of names and numbers. It organizes the data spatially using complex algorithms like geohashes. When the driver assignment service takes your job, it doesn't scan the whole city. It goes to the cache and runs a hyper-specific spatial query.
Like drawing a map.
Exactly like that. It basically draws a digital bounding box or a circle on the map. It says, here are the writer's coordinates. I don't care about the rest of the world. Return every single driver currently inside a 2-kilometer radius of this exact point.
And because the data is structured spatially in the RAM, it doesn't even look at the drivers 5 miles away.
Yeah.
Gets that answer in milliseconds.
Instantly, it gives the assignment service a localized list of, say, 10 eligible drivers right near you. And this brings us back to a huge foundational design principle, using the right data store for the right access pattern.
Right.
You use the durable relational database for long-term historical records that need to be perfect. You use the screaming fast in-memory cache for the fleeting, hyperactive present moment where speed is absolutely everything.
Okay, so the assignment service has its localized list of 10 nearby drivers. It runs its algorithm, maybe factors in their current ratings, what direction their car is facing so they don't have to make a U-turn, who's been waiting for a fare the longest. And it picks one.
It finds the one.
It says, driver X is the absolute perfect match.
Oh.
Now, my friend, we have arrived at the climax of the architecture.
We have.
And here's where it gets really interesting. I want to build a little narrative tension here.
Oh, go for it. Let's see the chaos.
Okay. I am standing on the rainy curb. I request a ride. But what the system doesn't know is that 50 feet down the exact same block, another guy is standing in the rain, and he taps request ride at the exact same millisecond.
It happens all the time after concerts or sporting events.
Right. We are in the same location, and let's say it's late at night, and there's only one available car within that entire 2-kilometer radius. We're both fighting for the exact same physical car. What happens?
You have just described the classic race condition in distributed computing. This is the failure mode that keeps back-end engineers awake at night in cold sweats.
Walk me through the disaster first. What happens if they didn't anticipate this?
Okay, so remember how we said earlier there isn't just one single computer running this whole operation? To handle global scale, there are dozens, maybe hundreds of physical servers running parallel instances of the driver assignment service.
So they can handle thousands of requests globally at the same time.
Exactly. So your request from the RAN goes to assignment server A. The other guy's request down the block goes to assignment server B. Both servers query the driver location cache at the exact same millisecond.
What does the cache say?
The cache looks at the map and says to both of them, there's only one car nearby, driver X.
Uh-oh. I see where this is going.
So server A looks at the data and says, great, driver X is the best match. I'm assigning him to the first rider. Simultaneously, server B looks at the exact same data and says, great, driver X is the best match. I'm assigning him to the second rider.
And because they are independent servers running in parallel, they are totally blind to what the other is doing.
Exactly. They don't talk to each other. They're just doing their jobs. So they both send a message to the main database. Update driver X to matched status. They both send a message back down the chain to the gateway. Your app suddenly flashes, driver X is on the way. The other guy's app flashes, driver X is on the way.
And poor driver X.
His phone receives 2 conflicting navigational routes on the screen at the exact same time. It's a complete double-booking nightmare. It breaks the real-world experience, it shatters trust, and honestly, it ruins the product.
It's exactly like trying to buy the very last ticket to a Taylor Swift concert online.
Yes, perfect example.
You click buy at the exact same second, someone in another state clicks buy. Or trying to select that one specific aisle seat on an airplane when another passenger is looking at the exact same seat map on their laptop. If the system doesn't coordinate, you both think you got it until you show up at the venue and someone is sitting in your lap.
Exactly.
But wait, if server A and server B are totally blind to each other, you can't just let them update the database whenever they want. Do they have to check in with a master server first, like some sort of digital referee?
You've hit the nail on the head. That digital referee is the star of this step, the distributed lock.
The distributed lock. How does the digital lock work across hundreds of independent servers?
It acts as a system-wide mutual exclusion mechanism. It is a neutral third-party referee that sits entirely outside of the assignment servers. Before any assignment server is allowed to actually claim a driver and send the notification, it has to reach out to this distributed lock, which, by the way, is also often managed by ultra-fast software like Redis, and request explicit permission.
So server A and server B both find driver X in the cache, but before they can finalize the match, they have to race to the lock.
Exactly. It's a literal foot race. Server A asks the lock, can I have the exclusive rights to driver X? Server B asks the lock, can I have the exclusive rights to driver X? But the lock is single-threaded.
Meaning it only listens to one person at a time.
Right. It processes requests strictly sequentially. Even if those requests arrive a microsecond apart, one of them objectively gets there first. Let's say server A wins the race by a fraction of a millisecond. The lock says, yes, server A, I am locking driver X. You hold the key.
And what happens to server B?
Server B arrives a microsecond later and hits a brick wall. The lock replies, sorry, driver X is currently locked by another process.
Denied.
Denied. Server B is immediately blocked. It realizes the driver is taken, drops driver X from its list, and is forced to go back to the cache to find the next best car for the other guy. Driver X only ever receives one request. Your app shows the car coming, and the other guy's app keeps saying, searching for a few more seconds. Crisis averted.
That is amazing.
Yeah.
But as I look at the design notes here, they call this surgical precision. The engineers seem very proud of how sparingly they use this lock.
They should be.
But why not just put locks on everything to be safe? Why not lock the rider's profile, lock the map data, lock everything?
Because locks are the absolute enemy of speed. Every time you force hundreds of blazing fast parallel servers to stop what they are doing, pause, and politely wait in a single file line to ask a referee for permission, you introduce latency.
You're creating a bottleneck on purpose.
Yes. You slow the entire ecosystem down. If you put locks everywhere, the massive parallel processing power is wasted, and the system basically crawls to a halt.
Ah. So you only use them when absolutely necessary.
This is the design principle of coordination only where contention actually exists. Autonomy is speed. You want to avoid locks at all costs. You decouple, you use asynchronous streams, you let servers run wild and free, making decisions in parallel, right up until the exact, inevitable choke point where a literal physical resource in the real world, a single human driver, is being fought over.
Surgical precision.
Only at that moment do you apply the lock. Surgical precision.
Okay, so the system fought off the other servers, claimed driver X, and locked it in. The backend knows the match is made. But the driver is just sitting in their car, totally oblivious.
Right, they don't know yet.
How do we actually wake up their phone to tell them? The assignment service hands the match job over to a notification service, and the notification service has to alert the driver. Now, looking at this, it explicitly points out that it does not use a WebSocket for this initial alert. It does not.
It uses a push notification. Why change tactics? We spent the whole first section talking about how amazing WebSockets are for real-time updates. Why not just whisper down the open phone line to the driver?
Because you have to account for unpredictable human behavior and the strict limitations of mobile operating systems. Think about what a driver is doing when they aren't actively on a ride. They are sitting in their parked car, waiting. Are they staring blankly at the Uber app for 20 minutes straight?
Probably not. They're probably checking their email or scrolling through Instagram or reading the news.
Exactly. The ride-sharing app is pushed into the background, and both Apple's iOS and Google's Android are incredibly aggressive about battery management. They have to be.
Right. Nobody wants a dead phone.
If an app is sitting in the background for too long, the operating system effectively puts it to sleep. It freezes its background processes and completely severs its network access to save battery life.
Oh, it's the WebSocket.
That beautiful, persistent WebSocket connection we talked about. The phone's operating system likely killed it 10 minutes ago. So if the server tries to whisper down the WebSocket, hey, we found a writer, nobody is listening. The phone line is dead.
Exactly. The message would just disappear into the void. A push notification, on the other hand, is explicitly designed by Apple and Google to solve this exact problem. It is a specialized, high-priority signal that operates totally outside of the app itself.
Oh, I see.
It bypasses the sleeping app and talks directly to the phone's core operating system.
It's a digital poke in the ribs.
Yes. The notification service sends the payload to Apple or Google's push servers. The operating system receives it, wakes up the phone screen, sounds that familiar chime, and says to the driver, hey, wake up, there's a ride request.
Okay, so the driver hears the chime, they look at their screen,
Yeah.
and then the blueprints show that the driver also has a persistent connection back to the gateway.
Right, because once the driver hears the chime, they tap the notification, the operating system pulls the app out of sleep and back into the foreground, the app springs back to life, and the very first thing it does is immediately reestablish its own WebSocket connection with the gateway.
Back on the open phone line.
Exactly. Once the driver taps accept, the heavy lifting of the push notifications is totally done. From that moment on, for the entire duration of the trip, both you and the driver are communicating with the server via those open WebSockets. Live GPS updates, route changes, cancellations, it all streams in real time over those persistent bidirectional connections.
And the loop is closed. The match is made. I mean, 3 seconds after I tap the button in the pouring rain, a driver a mile away gets a ping, accepts, and starts heading my way.
It's truly breathtaking when you pull back the curtain and lay it all out like that. We have walked through the weeds, we've seen the microservices, the data strings, the spatial caches, the locks. So, let's step back. What does this all mean for how we build technology today? I'd love for you to synthesize this for us. What are the core laws of distributed systems that this specific architecture reveals?
I think there are 5 unbreakable laws demonstrated here, and they apply to almost any massive system being built today.
Let's hit them. Number 1. Decoupling via async messaging. We saw this with the Kafka event stream in the driver assignment queue.
Right.
Whenever possible, you trade the comfort of an immediate response for the safety of massive resilience. You don't want systems waiting on hold for each other. You want them leaving messages on an indestructible answering machine and working independently, so if one component catches fire, the whole house doesn't fall down.
Right. You build shock absorbers into the system. What's number 2?
Number 2, the right data store for the job. We saw the stark contrast between the durable PostgreSQL database and the in-memory Redis location cache.
The filing cabinet versus the sticky notes.
Exactly. You don't shove all your data into one giant filing cabinet. You use traditional databases for history, financial integrity, and absolute truth. And you use blazing fast RAM caches for the fleeting high-volume present so your hard drives don't physically melt down.
Match the tool to the access pattern. Got it. Number 3.
Number 3. Coordination only at contention. This is the surgical use of the distributed lock.
The referee.
Right. Autonomy is speed. You let your servers run wild and free, making decisions in parallel, and you only force them to stop and coordinate at the absolute last microsecond when a physical, real-world resource is at stake. Locks are strictly necessary for correctness, but they are toxic for speed.
The Taylor Swift ticket rule. Don't lock the whole website, just lock the specific seat. Love it. Number 4.
Number 4, real-time pushover polling. This is the WebSocket principle. Stop wasting battery and bandwidth, having clients constantly ask, are we there yet? Is it done? How about now?
The annoying kid in the back seat.
Yes. Build systems that allow the server to push the answer the instant it's known, keeping the phone line off the hook.
Yeah, it's just a vastly better user experience. Yeah. And finally, number 5.
Number 5, fan out. We saw this with Kafka's consumer groups. Design your events so that they are public broadcasts, not private direct messages.
Shouting into the void.
Shouting into the void. When something happens in your system, broadcast it to a stream so that multiple independent services, the ride matcher, the analytics team, the fraud detection AI can all learn from the exact same event simultaneously without creating complex, tangled dependencies on each other. Let everyone listen to the radio station independently.
It's an absolute masterclass in managing complexity. Thank you for walking me through this today. And to you, the listener, thank you for coming on this incredibly dense, rewarding journey through the architecture of a single tap on your phone. Next time you request a ride, you'll know exactly what kind of invisible digital symphony you just conducted.
It really is a symphony. And, this raises an important question, something I actually want to leave everyone with as they go about their day.
Okay, let's hear it.
We just spent this entire time looking at how a global tech giant goes to these extreme lengths to decouple tasks, avoid bottlenecks, and isolate failures in their computer systems. But how often do we fail to apply these exact same principles to our own human systems?
Oh, wow. That's really interesting, taking back-end engineering and applying it to life.
Yeah, think about the way your office operates, or how your family coordinates a really busy week. Where in your life are you pulling for information? Constantly checking in and asking a coworker, is this done yet? Instead of agreeing on a push notification, like, just ping me when it's ready.
I definitely do that way too much.
We all do.
Hmm.
Where are your human bottlenecks? What projects in your life need to be decoupled so that one person getting sick doesn't derail the entire team? Do you have human processes that need a distributed lock to prevent double booking your own time? I'd really challenge you to look at your own daily workflows, your own routines, through the lens of a distributed system.
That is brilliant. So the next time you are standing on a curb in the rain, waiting those 3 seconds, maybe ask yourself,
Hmm.
is your own life running as smoothly as the software finding your car? A lot to think about. Until next time.